Next time you look up and see a massive commercial airliner cruising effortlessly through the clouds at 500 miles an hour, think about what it actually takes to keep hundreds of tons of metal suspended in thin air. It's a stark contrast to how this all started. In 1903, the very first powered airplane was essentially a giant, fragile wooden bicycle held together by canvas and wire. On its first successful attempt, it hopped over the sand for barely 12 seconds. While people had been experimenting with wings for years, the Wright brothers were the first to build a system that actually let them steer. By using cables to tilt the wings and move the tail, they proved that a pilot could point the nose, roll the body, and turn the craft. Powered flight was finally controllable. Getting off the ground was a breakthrough, but it also started a global engineering challenge that has lasted for over a century. Over the next 12 decades, airplane designers would have to find a way to balance three competing needs: speed, size, and efficiency. The first hurdle was the airplane's body itself. Wood and fabric were far too dangerous and weather-sensitive for everyday transport. By the 1930s, engineers solved this by building planes entirely out of strong, lightweight aluminum. Now, aircraft were durable enough to safely carry paying passengers. But these metal planes relied on spinning propellers, and propellers have a hard physical speed limit. If they spin too fast, the air passing over the tips starts causing violent shockwaves. To fly faster, aviation needed an entirely different kind of engine. This animation shows how a jet engine solves that problem. It works in 4 simple steps. First, the massive fan in the front sucks in a huge amount of air. Second, a series of spinning blades squeezes that air down until it is highly compressed. Third, fuel is sprayed in and ignited, creating a continuous, powerful fire. Finally, that superheated air blasts out the back. Notice the massive arrow pointing forward. That heavy blast of exhaust shooting backward creates an equal and opposite force pushing the airplane forward. This continuous thrust generates far more power than a spinning propeller ever could. By the 1950s, this jet power was attached to commercial airliners. Almost overnight, planes doubled their speed and could fly high above turbulent weather, giving passengers a remarkably smooth ride. Jet engines conquered altitude and broke the speed limits of the propeller. But that massive leap forward gave engineers a difficult choice. With all this power available, in which direction should they take the future of flight? In the 1970s, aviation reached a major crossroads, and engineers had to choose between 2 completely different paths. Should they use jet power to fly faster than the speed of sound, or should they use it to build massive flying hotels? On one side, there was the Concorde. Cruising at twice the speed of sound, it allowed passengers to cross the Atlantic Ocean in roughly 3 hours. On the other side, there was the Boeing 747 jumbo jet. It featured an iconic upper deck and a body so massive it could carry over 400 people on a single flight. This chart compares the economics of both planes. The Concorde burned an enormous amount of fuel to carry only 100 passengers. Because those fuel costs were split among so few people, airlines had to charge thousands of dollars for a single seat just to break even. Now look at how the data shifts for the 747. Because it carried 4 times as many people, the fuel cost was spread across hundreds of seats. The cost to fly a single passenger dropped dramatically, allowing airlines to sell affordable tickets to millions of people while still making a profit. That economic reality is why efficiency ultimately won. Travelers didn't necessarily need to cross an ocean in 3 hours if the ticket was too expensive for them to afford. They chose reliable access to global travel, even if the journey took a little longer. Once efficiency became the goal, engineers looked for ways to make planes lighter and smarter. In the 1980s, heavy physical cables and metal pulleys were replaced by fly-by-wire systems. Instead of a pilot physically pulling a cable to move a wing flap, lightweight computers interpreted the pilot's commands and adjusted the wings automatically. Then came the materials revolution of the 2000s. Just as the industry had swapped wood for aluminum decades earlier, modern aviation began replacing heavy metal with carbon fiber. These are high-strength threads woven together and baked into tough, lightweight panels. You can see this shift in modern jets like the Boeing 787 Dreamliner. Its seamless body and highly flexible wings are built extensively out of these carbon composites. Carbon fiber provides three major benefits. It makes the entire airplane significantly lighter, which means the engines burn far less fuel. And because the composite hull is so strong, airlines can safely keep the cabin more humid and comfortable for passengers. It is remarkable to look at these massive carbon fiber machines and realize they trace a direct line back to a wooden glider over a sandy beach. That 12-second flight proved that human beings could carry their own power through the air, a concept that now allows us to reach the other side of the planet in less than a day. The history of flight shows that raw speed wasn't enough. For aviation to work for everyone, engineers had to build machines that were safe, affordable, and capable of reaching every corner of the Earth. Airplanes are the result of over a century of constant refinement. As we look ahead, what do you think the next century of flight will look like? Could fully electric planes become the new norm? Share your predictions in the comments below. And thanks for watching.